So here I have another example for a linear model exploration. So for your application, you have some data sets to choose from. Each quarter I mix it up a little bit. So if you're watching this video, it may or may not be this exact list of data sets. So check the instructions on your version carefully. So what we want to do is go to one of these data sets. In the data set, pick a couple of quantitative variables and see if there's any kind of correlation between those variables. Do the points kind of line up? If they do, then you'll continue trying to write up an essay where your essay meets the points listed here, and you're going to have a little bit of some graphics to go with it. It's important that in order to answer the questions and describe what the linear regression model means, that you have to know what the variables mean. So you better check the online descriptions, either in Appendix B in the book, or go to the online descriptions from the course, the book website. So I have that here. And so I'll have to look that up in a moment once I pick a data set. So the data sets, this is a link to my Google Drive folder of data sets, and mostly they're what are called CSV, comma separated value files. For some of the ones that I use often with the class, you'll find a Google Doc version of it. If you do go and open one of those Google Docs, since it's my Google Doc, it'll be view only for you. So instead of seeing all the Google menus as shown here, your version will look more like this in the view only mode. And then you will have to make a copy so you can edit your own. Now, once you pick out the right data set for you, and you may decide to change, so I'm going to do this one here, then you have to play around and pick a couple of variables to work with. I highly recommend that you first make a copy by duplicating the sheet. Then you'll get a sheet next to it at the bottom called copy of whatever it was called. This way you don't accidentally screw things up. So every once in a while I'm exploring a data set and I accidentally mess up the data somehow. So I want to be able to get back to the original in case I do mess up the data. So first thing you should do is make a copy. And then in that copy tab down here, right, so now I've made two copies, right? First I made a copy of the whole spreadsheet file. Then I made a copy of the data tab down at the bottom. And then I explore. I want to try to find a couple variables. So I can see there's a variable age here, and age is definitely quantitative. I have a variable called height. Height's quantitative. Foot. What is foot? Okay, so now I don't really know, so I better go look up the data set. So I'm looking for a data set called PA seniors. They're alphabetically listed. PA seniors is on page 67 here. All right, so information on a sample of high school seniors from the state of Pennsylvania, 2010 through 2019. The data frame contains 457 observations with 36 variables, and here's the descriptions of the variables. And down at the bottom, they tell us more. And if that description isn't quite enough, you can go find the data source and look some more. So often when I look up a summary of data, I find that what they told me about the data set isn't sufficient. I need more information. So I'll go back to the original article where the data came from and see if I can get some more information about it. Like maybe I want to know what kind of sample was it? Was it a simple random sample? Maybe, probably not. Was it stratified in some way? Was it a cluster sample? There's all kinds of samples out there. And I may just want more information. So this data set gives responses for a random sample of high school seniors in Pennsylvania who participated in the Census at Schools project. Okay, so it's random high school seniors. Now, it's probably not all high school seniors. If they were participating in the Census at Schools project, that means they were probably in a math class where the teacher decided to use this curriculum. Or it could be that the Census Bureau reached out to high schools and asked certain high schools to do this with them. So if we wanted more information about how the sample came about, we could go over to the Census Bureau website here, amstat.org, and read more about it. So sometimes we do need to do that. I was just kind of curious about what foot meant. Foot length in centimeters, okay. Height in centimeters. Oh, that's good to know. For some reason, I just assumed inches without really thinking about it. Danger, not thinking. Okay, so read the details, think about what it means. Okay, yeah, 165 inches, that's nuts, right? Yeah, centimeters, that makes more sense. Arm span, 161 centimeters, that makes more sense. Okay, so maybe I say, well, you know, as somebody grows older, they get taller, so I might want to take these two variables. Normally, when you select columns, they're connected. If you want to select disconnected columns, what you do is select the first one, hold the control key, and then select another one. So control lets you select stuff that's not connected. And then I just want to take a peek. Does that look like it might be? So we want a scatter plot, not a column chart. That's meaningless. Yeah, so you know that looks like nonsense to me. If you're not sure, you say, hey man, maybe there there is some correlation there. That looks like a linear cloud of stuff. So I'm going to go over to customize. I'm going to take a look at the series. I'm going to have it draw the trend line. And then I'm going to ask it for, now they won't give me the correlation coefficient R. They only give R squared here. And they're saying R squared is 0. So if you take the square root of 0, you still get 0. So this is crap. All right. Oh, well. Why was it crap? Shouldn't age correlate with height? The answer is yes, but the ages here, these are just high school seniors, so there's a very narrow age range. And you know, a lot of high school seniors, they're at their peak height. So what we should just find is that there's going to be a kind of a random kind of distribution. Nothing really is going to line up. So all right, so that didn't work. So I might try something else. So I'm just going to play around here. Maybe let's see, time travel. What was that? Time travel to school. Okay, so some kids have to travel to school versus reaction time. Hey, 2 times, maybe I could correlate those. So I grab those, they're right next to each other, pretty easy. I insert a chart, I ask for a scatter chart, and I get a cloudy mess, nothing there. Okay, if you wanted to double check the correlation, you could, but my guess is the correlation is gonna be pretty darn close to 0. All right, so it could be you go down some places that just don't work. Reaction time versus memory score. Oh, 2 things related to the mind, I think. Let's see, what do those mean? Reaction time, time in seconds to click when a color changes. Memory score, score in an online memory game. Maybe those 2 things are related. Let's see, reaction time, memory score, graph. Ooh, that looks like a cloudy mess. Might kind of see an uphill trend to that slightly, so maybe I'll go to series, throw the trend line on there. Just because you can put a line through it doesn't mean you should. R squared is pretty damn close to 0, 0.015. If we take the square root of that, SQRT of 0.015, I get 0.12. That's still pretty low. I'm going to say, nah, that's nonsense. No correlation here. Okay, so I struck out many times in a row here, and that happens. So the idea of we look for correlation if we think there might be a cause or reason the 2 variables might be connected. So I'm going to go for one I think I'm pretty sure is connected. The taller somebody is, the bigger their arms are. I'm as seeing humans around, I'm pretty sure that's true. So I'm going to check out height and arm span. So I could just highlight those, click column, control click the other column, control C to copy, throw those in a new tab, control V as in Victor to paste, and those are my variables. Now, I already grabbed these and started playing with it, so I'm just gonna bring this up here, maybe. There we go. Let's blow this up a little so we can see it better. One more time, perhaps. All right, so I chose height versus arm span, and I made a scatter plot, and then I, like before, drew the line through it. I made the line a little darker there. I got a little key that says the arm span of the blue dots, and the black line is this expression there. I calculated R, which is the correlation coefficient, and it's always got to be the Y values first, the X values second. That's super important. And then I did the slope, and again, slope, very important. Y values first, X values second. So column B, then column A, and B is my Y-intercept. And again, very important, intercept, Y values first, X values second. It turns out R is interchangeable for X and Y, but M and B are not. So if you get the order of Y and X wrong, you got the wrong slope and the wrong Y-intercept, you get the wrong line. Very important. So notice that my slope here matches the slope that the regression equation that Google Sheets picked for these points right here. And the points are kind of hugging that line. There's a little bit of deviation, right? So there's some relatively tall person here that has short arms, and then there's a relatively short person here that has long arms. So, you know, there's definitely deviation, but this looks like a pretty good linear model. So now I want to talk about what some of these numbers mean for the linear model. So let's go over to my notebook here. So again, we're playing with two quantitative variables, scatter plots. With the scatter plots, the points, we're trying to see, do the points kind of line up? That's called correlation. If there is some correlation, then I'm going to find a linear model, y equals mx plus b. Now, I usually only look for correlation if I think there's a reason, a cause that one variable affects the other. R is the correlation coefficient. R is going to be some number between -1 and 1. If it's a negative number, that means the points slope downward, like this here. As the x value increases, the y value decreases. If R is positive, that means it's going to slope upward. Now, R is not the slope. The closer it is to 1 or -1 means the points line up very well. There's not a lot of scatter. The closer it is to 0, the more scatter there is among the points, the less the points line up, and the more likely it is that there's not a causal relationship between the variables. So this is important. Correlation does not imply causation. Doesn't go that way. Yeah, so that's the basic idea there. So let's move on to this example here. So I just took that spreadsheet, made a little screenshot so I could scribble on it and type some more stuff up. The x value, the value on the horizontal axis, that's also called the independent variable or the explanatory variable, and I chose height to be that. So my idea was as somebody ages, they get taller, and I expect taller people to have longer arms, right? So that was my reasoning, that's my causation, and there is correlation here. Correlation means do those points, the height versus arm span of an individual, do they line up? So every one of these points, like this one right here, that's a specific person right there, right? That person has a height and an arm span. Over here, that's another specific person. They have a special height, and their arm span. Arm span, by the way, put your arms out like wings, fingertip to fingertip is the measurement. So my correlation coefficient is about 0.717. And so down here, I state what I believe that means, the interpretation, right? If you just say correlation is a linear relationship between two variables, it's strong or weak, this correlation is about 0.7, that's not an interpretation. You just tell me that's kind of like a definition. What does it mean in this situation? So because 0.7 is close to 1, I can say there's a strong positive relationship. Okay, so what? What does positive mean? Positive meaning that an increase in the height implies an increase in the arm span. Okay, so that's the positive relationship. Strong, I probably should have elaborated on that, just means the points aren't that scattered, they line up pretty well. So that's what I mean by strong. Now, slope is a little bit harder to interpret. You have to do some work. First thing you have to do is know what your variable means, and you can see I screwed that up here because when I looked at the data set said the height was in inches. No, I lied. I thought it was in inches. The height is in centimeters. So I got to fix this. So I have an error. Magic pen. That is centimeters. That should be centimeters. Or else do I have a mistake? And then down in the sentence, I'll fix in a minute. Okay, so X is height in centimeters, Y is arm span in centimeters. Slope is rise over run. What does it mean to rise here? Rise means an increase in arm span. What does run mean? Run means an increase in height. Okay, so that's what I'm writing down here. My slope is 0.915. To get a rise over a run, I got to write it as a fraction. So that'd be 0.915 over 1. So my numerator says 0.915 increase in arm span, and then 1 is the increase in height. So then I want to put that together in a sentence. Now this is important. The explanatory variable pushes the response variable to do something. So if somebody gets taller, their arms are going to grow also. So when I speak about the sentence for slope, I want to do the explanatory variable first, and then say what happens to the response variable. So I have, for an increase of 1, that should be centimeter in height, we expect an increase of 1 centimeter in arm span. So that's the interpretation of slope. Okay, and to interpret the slope, you got to do quite a bit of work to think about what it means. It's complicated. So think about that. Every time I interpret a slope, I have to go through all of this work to make sure I get a decent sentence. Y-intercept. Now the Y-intercept is a point on a number line. So the Y-intercept here is the point 0, comma, about 14. What does that mean? Okay, 0 what? 0 height. And 14 what? 14 would be the arm span. So this tells me that if somebody has a height of 0, their arm span should be 14 centimeters. Interesting, height of 0. How can someone have a height of 0, right? So I wrote that out here, and then I make a note here, this is not a meaningful interpretation, right? That's crap. Nobody has a height of 0. But if we didn't have that plus 14 centimeters here, then my line would be lower down here, and it wouldn't go through the points. So this is important. Although the interpretation of the Y-intercept is nonsense, I do need that number to get the line running through the right spot in the points. Otherwise, I would see the line sitting lower. If we just tried to delete that 14.199, then our line would be down here. And that line does not fit those points. It's too low. So that's important too. All right, last thing, predictions with an equation. So I have an equation, y equals 0.915 x plus 14.199. I went for 3 decimal places in rounding. Let's go over to the spreadsheet and look at what a prediction means. So let's scoop over here. All right, predictions. And to make a prediction, you pick a number for usually the independent variable, the explanatory, and then calculate using the equation the response variable. So I'm going to say, all right, let's pick like 175 centimeter person. So prediction X is 175. Then Y, I want to calculate based on this equation right there. So I'm just going to have to type that out. So equals the slope, 0.915. I can just type it, that's all right, times this X value right there, plus my Y-intercept, 14.199, enter. So this equation predicts that if we find a high school senior that is 175 centimeters tall, then they should have an arm span of about 174 centimeters. This right here, because my 175 is within the given data set, right? My data set ranges from about 130 to 200-ish. That number's in that range. This is what's called an interpolation. Is this a reasonable interpolation? Well, I have a pretty strong correlation here. And so based on the strong correlation and I'm doing an interpolation, I would say this is a reasonable prediction, okay? And you're gonna write something like that up in a sentence. Now, suppose instead I pick somebody with a height of 100 centimeters. Now, 100 centimeters is off the charts, right? It's way off the chart here. The shortest person I have is right there, and that person is 129 centimeters tall. If you pick an X or a Y value that's outside of the given range of data, that's an extrapolation, and extrapolations can be dangerous. It's like looking and predicting the future. That can be dangerous. We can do it a little bit with really good mathematical models, but there are limitations. So let's do the calculation. I can just fill this one down. Okay, so this says if I find somebody with a height of 100 centimeters, then their arm span should be about 106 centimeters. That is an extrapolation. The question is it reasonable? And the answer here is maybe. Is it within my realm of knowledge? The answer is no, I don't have data related to 100 or 105. Although there are some heights down here that are, let's see, we got 100, arm span 119, 120. Okay, so we have nothing as low as 105. So again, excuse me, this is outside of my realm of knowledge. It's extrapolating. And so is it reasonable? Maybe, maybe not. So again, reasonable. Answer is yes. Within data, strong correlation. This one right here, maybe outside of my data range. Outside data, but strong correlation. Now, again, this study was aimed at high school seniors. So, maybe I could apply this to juniors, maybe sophomores, maybe even freshmen. Could I apply it to people outside of high school seniors, like college seniors or someone that's in their 30s? And the answer is maybe. A lot of people stop growing around when they're a senior. Some people continue to grow into their early 20s, kind of depends. Would it be reasonable here for me to pick like 250 centimeters and then do a calculation? Okay, 250 centimeters. Think about that for a second. There's what, 2.5 inches in a centimeter. So if I take that 250 divide by 2.5 inches, since most of us are more familiar with inches, that gives me someone that's 100 inches tall. And if I take that and divide it by 12 inches in a foot, that's somebody that's 8 feet tall. Not many people that are 8 feet tall. And so that means they would also have an 8-foot arm span. I think that's a little way too far outside to even write down. All right, so I went over all the main points of this. Very important for me and you in this, that you not just do the calculations. With this spreadsheet pretty much does formula with the corresponding formulas. Spreadsheets are beautiful, right? It'll find the slope through all those points. The type of slope, oops, I messed that up. We're finding here is called a linear regression slope. This is talked about in the book. I believe it's section 2.6. One more quick example, and then we're out of here. So I did another example. I looked up some data on Oregon marriage rates in a given year. And in that same year, what was the percentage of engineering bachelor's degrees awarded to women? And it turns out, so each point is a year. The X value is the Oregon marriage rate. The Y value is the percentage of women who got an engineering, a bachelor's degree in engineering. And it turns out there's a reasonably strong linear correlation right here. I found R was 0.76. It was even higher than the last example. So I said, well, why not find a model here? So I did. I told the computer to give me the slope and the Y-intercept, and I have that graphed here also. X value, what is a marriage rate? I had to look that up. It's not a percentage, it's the marriages per 1,000 people. So if the marriage rate is 7, that means there were 7 marriages per every 1,000 people in that area. Okay. So Oregon marriage rate through the, this was around the year 2000 for, I think, 12 years. Marriage rate ranged somewhere between 6 and 8 marriages per 1,000 people in Oregon. Bachelor's degrees in engineering for women, that ranged somewhere between 18 and 21% in the same time frame. And again, each point is a particular year. So there's really 3 variables going around here. There's the year, and then the point in that year is the marriage rate and the percent of engineers that are women with bachelor's degrees. To figure out what the slope meant here, the 1.69, I had to remember slope is rise over run. My vertical variable here, the rise here, it would be an increase in the percentage of engineering degrees awarded to women. And the run here would be an increase in the marriage rate in Oregon. And these are all increases because the numbers are positive. If one of them were negative, it would be a decrease for just that variable. So the rise would be an increase in the percent of engineering degrees in women here. And the run would be an increase in the marriage rate. So we write that as a fraction, 1.69 over 1. And we always state the explanatory first and the response variable for second. And so you can see my sentence down here for that. So the slope tells us here that for a 1 out of 1,000 increase in the marriage rate in Oregon, there will be a 1.69% increase in the percentage of BA degrees awarded to women. Now, there is correlation, but is there a cause? Can you think about a reason why people getting married would lead to more female engineering degrees? I can't. So although I have correlation, there's no causation that I can reasonably come up with here. And again, this is Oregon versus the whole country. So that's another weird thing. So I found a model, but it's kind of crap because I really have no causation. Well, why would I even make this model, right? So just because I can make some kind of model like this doesn't mean I should. So this one right here is kind of meaningless. This one here is more meaningful. And so the two things you got to think about. One, is there a reason one variable, quantitative variable, might be related to another one linearly? Some data curves, that's a whole nother story. Another course in statistics, you could look at that. And then if we think there's a causation, can we mathematically find a correlation? Means do they really actually line up? And they may or may not, depends on the situation. Write stuff up in words, think about if your mom would get it and if I would get what you're saying without having to look back at the original questions. And write it up in an essay style, right? Don't answer the questions one at a time. Write it up nice, 2 or 3 paragraphs with pictures. All right, that's it for now. Take care, do good math. I'll see you in the near future.